moment.
Okay. Today, I want to talk about concreteness, about concrete categories. I want to prove that homotopy category of model category usually is not concrete, and we start with the definition. What is a concrete category? Definition. Category C is called concrete if there exists a faithful functor U from this category to the category of sets, and this functor is faithful. Recall that faithful functor is such one which is bijective on morphisms. Okay, and what are the examples? The first one is trivial. This is a category of sets. The next is any small category is also concrete. Any small category is concrete. Small category is such category which has a set of objects. Okay, and why is it true? It's simple, because for any object B from C0, we can define U of B as a set of morphisms which end at B. Is a set of such morphisms. Okay, and U of the arrow is the following one. We take the arrow, some arrow, and we obtain and we take the composition with this arrow. And we have the following. Okay, we can think about the functor U as a forgetful functor. And the second example, when P is a pose set, then we have the following functor D from this category to set, which sends X to the following set, such A from P, which are less than X, and we on morphisms we have the following function. Okay, the third one is a set of categories of concrete categories. We know that the category of topological spaces is concrete. Also, the category of monoids, groups, R modules, rings, and so on. We can think about concrete category as a about set with the additional structure. Okay, and the last example is a category of small categories. Okay, and there is interesting question. Is it true that there is a non-concrete category? And the answer is yes, and Freud proved this result in 73 theorem by Freud. The category, the homotopy category of topological spaces is not concrete. Philosophically, why it's true? Because of we have a lot of morphisms in the localization at weak equivalences is a class of zigzags, and we have a lot of such zigzags, and this is why this category is not concrete. And also we identify different arrows, and but for a strict argument we need the following definition. Definition of a regular generalized subobject. What is it? Let F be is a be morphism from the slice category over A is a object, the object of slice category, and suppose that this class is the class of pairs UV from A to B. A and B is are objects of category C, such that we have the following diagram. And this diagram is commutative, but it is not equalizing. Just a commutative diagram. Okay. And then we say that f is equivalent to g if and only if the following classes are equal. For any B object of the category C. Okay, and then we define the regular generalized subobject as a factor is a factor category. We should consider this category with respect to this equivalence relation. And so we say that this one is a regular generalized subobject. Okay. The next proposition tells us that if C is concrete, then this class of regular generalized subobjects must be a set. For any A. This I don't want to prove this proposition. It is simple, but I think that we can skip it. Okay, and now by means of this proposition, we will prove the Frey theorem. But we need a technical lemma. There exists a sequence of abelian groups, say B. For any ordinal alpha, B alpha is a abelian group. Abelian group with a p torsion. Okay, such that we have the following conditions. The first one is each B alpha has an element for any B alpha. There is a X alpha which is not equal to 0, such that this is a p torsion. And the second one for any homomorphism. F from abelian group by beta to B alpha with beta greater than alpha, we have that the image over x beta under f is 0. Okay, this can be proven, but you can find the proof and details in article. But I think that it's not interesting, and we also skip the this proof. We can think about this lemma as a black box lemma. Okay, and now I want to use the following notations. Let M be alpha n is denotes move space. And let T alpha is a homomorphism from this group to the alpha, such that the image of T alpha contains X alpha, and let U alpha is the induced map from the first move space to the second, which corresponds to the group ZP and B alpha in degree n. And also is induced map induced by this homomorphism. Okay, then we can form the following sequence, the following exact sequence. Cofabration sequence. We can start with U alpha, and we take the cone of this morphism U alpha. This is a cone of U alpha. And after that, we can repeat this process. We can take the cone of this morphism, and we will obtain this one, and so on. This is a cofabration sequence of the map from M to M alpha, and we can notice that these spaces are also Moore spaces. Proposition C alpha is also Moore spaces. Then it has the following presentation. Okay, and I wanna prove this this proposition. It's very easy. We have the following induced sequence of Moore spaces. M. Suppose that we have this sequence in the category of groups K, G, say, and co-kernel of this this map, say delta, and say this map is a gamma, and then we can form the cylinder of the map gamma, but we know that this cylinder is homotopic to this Moore space, and then and now we I want to consider the following pair of topological spaces. The following pair of spaces, say MKM and the cylinder of gamma. We know that the first space embeds into the cylinder, and it is a good pair. It is a Borsuk pair, or and inclusion also is a cofibration, because we can think about this inclusion as a inclusion of subcomplexes. This is a subcomplex of this one, CCW complex. Okay, is a good pair, and then we can write the long exact sequence of this pair, and we will obtain that the first claim is this homology of a pair is the same as a homology of quotient, because of goodness of the pair. Okay, and also, but we know that this is the same as a cone of the map gamma. Okay, and by long applying long exact sequence of pair, we obtain the proposition. Okay. Okay. Now we know that the cone of this map is also Moore space, and after that consider the following proposition. Our aim is to prove that the set of such morphisms, class of such morphism, is a pure class. It is not set. We want to prove that these arrows are different with respect to the equivalent relation which we introduced before. And for this purpose, we should prove these propositions. The first statement is proposition number 1 says that the composition can't be this composite can't be homotopical to 0. Okay, let's prove it. If it is not so, then we have the following morphism from this. We have the following morphism of the diagrams. This is the first diagram, and the second diagram is just a cone. We have a cone. This is a cone, and the composite of this map is homotopical to 0, and we have morphism from this diagram to the second diagram. And then we have this square, and if we take homology, nth homology of this square, we will obtain a contradiction with the black box lemma. If I take the factor hn+1 of this square, then we will obtain the following diagram. But this diagram is not commutative, and because we on the one hand we have that this element maps to x beta maps to 0. But this arrow doesn't map to 0, and it's and it contradicts and this contradiction and the proof. Contradiction with the black box lemma. Okay, and now we're ready to prove the theorem proposition number 2. Morphisms V alpha from C alpha to M form pure class form generalized subobject, which is not pure class, which is a pure class but is not a set. Okay, let's prove it. Suppose that V alpha is equivalent to V beta for alpha is less than beta. Then we have the following diagram. And we know that V alpha and V beta are equivalent, and then we know that the composition, these compositions are the same in the category with the in quotient category, and category with the equivalences, but we know that this composition is trivial in homotopy category, because it's just composition in cone. And then we know that this composition, sorry, yeah, is homotopy trivial, but it contradicts with the proposition, with the first proposition. Okay, and now we want to generalize these results to abstract model categories, and for this purpose we should define homotopy groups with coefficients. In abstract model category, we can define this usual topological functors in the following manner. We can form homotopical colimit of this diagram. Is a colim. Suppose that our model categories are pointed, that is initial and terminal objects are equivalent. Okay, and we can take colim of this diagram and will obtain suspension of X. And also we can form homotopical limit of the following diagram. And it will be reincarnation of the loops omega y is a colim. Okay, and these functors are joint. We have two functors. Suspension. These are joined in homotopy theory with respect to the model category. Okay, then we can define homotopical homotopy groups with coefficients. Coefficient are some objects in our model category, say A, and we take this functor, we apply this functor to X, and this by definition is a home set in the homotopy category of M from A to iterated loop space of X. For A from and okay, and this group Pn is a group when n when A is greater than 1, and also it is a abelian group when n is greater than or equal to. And in this setting, we should have the analog of the Freight condition. Freight condition is previous lemma. This proposition is called the Freight condition. This is a Freight condition, but we can dually we can formulate the co-Freight condition, and for doing that, we consider no regular generalized object, but quotients. And in the same way, we say that we have a proposition co-freight condition. If C is concrete, then the class of generalized regular quotients Q of C A and A over of this slide category is a set. Dually, we should have classes which co-equalize arrow F, but it is not a co-equalizer, but we have that this class consists of such arrows UV such that composition F with U and F is with F with V are the same. And also we define this guy as a quotient category. We take category. We take this slice category with a equivalence relation, and after that we'll obtain the following one. Okay. But in this setting we have a problem with the black box lemma, because we have a contravariant conditions, and in the setting we consider the map from B alpha from the black box lemma to this group. Not this. Yeah, it's okay. It's okay. No, sorry, not this group, not this one. Is a group, is a quotient Q by Z. This group is divisible, and every abelian group can be embedded in this divisible group. Is a property of divisible groups, but I want. Yeah.
What do you mean that any abelian group can be embedded into this group? Any finitely generated or countably generated, or because clearly there are just groups with great cardinality in this group.
Yeah, thank you. B alpha is finitely finitely generated, I suppose. Yeah. Okay. Yeah, thank you. And now formulate the following definition, which is important for the following theorem. Let M be a model category and C is any category weak classifying object for M with respect to omega functor omega from homotopy category of M to C is a functor. Functor K from the category C to whole M such that the composition of these functors is a full functor. The second condition is there is a natural transformation epsilon from this composition to the identity functor, which is an epimorphism on objects. And we say that this is a right weak classifying object. And if there is a natural transformation eta from the identity functor to the composition, that we will call it which is a monomorphism object-wise. It is a left weak classifying object. The main instance of this abstract definition is the pair consists of homotopy group functor and Ellenberg-MacLane functor. Definition: if model category M has a weak classifying object with respect to Pn by n, then we say that M has a weak classifying object of type n. And the second functor, we will for him we will use the following notation as for Ellenberg-MacLane space. Okay, when M has a weak classifying object of a type n, For example, when this functor has a faithful left adjoint. The second case, when this one has a full right adjoint. Okay, and now we can formulate the following theorem. Let M be a model category. Pointed model category. And if there exists a weak classifying object of type n, when n is greater or equal to 2, then homotopy category is not concrete. Okay, introduce the following notations. Let K alpha is a like Ellenberg-MacLane space. B is a group quotient. K is a Ellenberg-MacLane space of the quotient, and C alpha has a homomorphism, is inclusion of B alpha into this divisible group, such that C alpha of X alpha, of course, is not equal to 0, and U alpha and U alpha is an induced map. Then we can, in this setting, we can consider the following sequence, the following fibration sequence, or Puppe sequence. We start with the fibration. We have a fiber F alpha, and we move to the left and take the loop functor, and we want to say that this class of arrows is a proper class. And if we are done, then a homotopy category of the model category in this setting is under the conditions of the theorem. We will obtain the proof of this theorem, of course. Proposition if we have this inequality, then the composite is not homotopically trivial. Proof we can form also in the same way in the following diagram. Suppose that it is not the case. Then we have the following diagram. Is a part of Puppe sequence. And denoted by phi, for example. Okay, then we can take p by nth, and we will have the following diagram. This triangle is commutative. Also we have natural transformations which can be used here. We have a natural transformation epsilon alpha from the composition of factors. And we know that these natural transformations are object-wise surjective. And then we can construct the order arrows, and also we can form the arrow psi, and the order triangle must be commutative. But it is not. It's impossible because of the construction of the group, the groups B alpha, B beta B as before, as we see as before, and we have a contradiction, and we are done. Okay. Now the last proposition, which is an analog of the second proposition in the Freyed theorem. When we proved the Freyed theorem, we used we use the second proposition, and this one is a analog of this one. This quotient object contains pure class. It's very easy if we have this diagram. We suppose that V beta and V alpha are equivalent, and then we have the following diagram. And from definitions, we have contradictions with the fact that this composition is not homotopical trivial. Okay. Now, I want to give some examples of non-concrete categories. Examples. The first one is consider category of chain complexes with non-negative non-negative graded chain complexes over Z. It is a it has yeah.
I have certain problem because if we assume that each group B alpha is finitely generated, then there could be only a limited number of different groups.
Okay. I now just a second.
I think maybe you don't need the fact that it embeds into the group Q mod Z. You just need the fact that there is some homomorphism which is non-zero on this element X alpha, which is certainly true for any abelian group.
Yeah, it's we have no embedding. Yes, we have no inclusion, but yeah, our main is have some element with which survives in the image. Yeah, but just a second. Yeah, we want to find some elements, and we can embed this I suppose cyclic group into this divisible group. We have a map such that this map doesn't vanish on X alpha. Yeah, it's not inclusion. Thank you. It's not inclusion. It's not inclusion. Yeah, and also B alpha is not finitely generated. Okay. Okay. So sorry for this trouble, but let's consider the following examples. The first one, when we take the model category of chain complexes, then we have HN, which is the same as pi m, has the following weak classifying objects. Which sends our group G, our abelian group G, to the following chain complex. Recall that HN is a function from this category to the category of abelian group, and this one from the category of abelian group into chain complexes. Okay, the second example. Simplicial sheaves on a side. Assume that we have a small Grothendieck side. Recall that site is a small category endowed with a Grothendieck topology. Grothendieck topology is a it's just a class of just a class of covering sieves or function which produces the arrows for each u. We have the following arrows, which are called covering sieve. Okay, we can think about this thing as a topological spaces with covering, with covering, where covering is just a subset of open subset of topological space. Okay, and also we can define hypercomplete infinity stacks. Consider the following category of press sheaves in the simplicial sets, endowed with a projective model structure. And on simplicial sets, we have a Quillen model structure, Quillen model structure. And this model structure is called global model structure. Okay, and now we want to localize this category with respect to the weak equivalences, which by definition are isomorphisms on pi n's. What is a pi n's? Pi n's are homotopy sheaves of a simplicial press sheaves. We have we want to define.
I'm sorry, can you explain once again, please, what is a global model structure?
Global model structure is a projective model structure on press sheaves in simplicial sets, and on simplicial sets we have a standard
so it's just another name for projective model structure.
Yeah. Another name of projective number structure of this in this category. Yeah.
Thank you.
I want to define pi n's as the following, in the following manner. Suppose that we are given a press sheaf, say F, and we want to map as a sheaves category. The first step is a composition with the ordinary pi n's, which lives in simplicial sets. This is just as a composition press sheaf F with the pi n's. Okay, and then we'll obtain we will be in the following category, and this category has a sheafification, the standard standard operation. And we have a sheaf.
So I guess if you want to be rigorous about it, you need to apply plus construction 2 times to obtain sheafification.
2 times.
Or you can just write, I don't know, A or something like that for sheafification.
Yeah. I don't know. Say J, for example. Yeah. You mean that there is a clash of notations?
Yeah. I mean, it's just usually plus means that we use this plus construction on sheaves. And,
let G will denote the sheafification factor, and then we have a and then we will map into the category of sheaves on C with the Grothendieck topology. This is also the clash. I don't know. Okay, and oh, sorry. It's true for n equals 0. Then p pi 0 is a set, so not a group. And if n is greater than 1 or equal, we have we should take the following composite. And we will have the price sheaf in the category of groups. And after that, we apply the sheafification. And we have the following category. Okay, the composite is said to be homotopy sheaves of a simplicial press sheaf F. Okay, and then if we have a natural transformation or just morphism between press sheaves, then we say that this is a local equivalence if we have isomorphisms on pi n's. Okay, the category. This category produces the homotopical category, homotopy category. But by means of localizations under this local equivalence. And we will obtain this homotopy category, and it's not concrete. Why so? As we have a functor omega n, which is a composite of the functor gamma and pi n. Gamma is a global sections of global section factor. And this functor from this composite from the category M to the category of pointed of the following slice category. And this one gives we classify object of type n. Okay, in this example, we use the modification of the main theorem, but this modification can be proven in the same way. Let us formulate the theorem. If M is quasi-stable, quasi-stable means that the composite of suspension and looping functors is full functor. This composite is full quasi-stable, and it has a general weak classifying object for some functor omega into the category of groups, such that the composition is object-wise epimorphism. Then then homotopy category is not concrete. Okay, and now I have no time, I suppose. I think, but I give I give an additional example. The third one is the category of localization of the category of spectra. Bose-Field-Friedlander localization. of spectra. And in this case, the weak classifying object is a functor homotopy group of spectra. This is a this functor has weak classifying object, and this weak classifying object is a Ellenberg-MacLane space. Okay, I think that's all. What I want to say, what I want to talk about. Have any questions? And this result is just this result by Ivan Di Liberti and Fosco Lareggia. Okay.
Yeah, maybe I have kind of a, I don't know, a question. Can something similar be done for, I don't know, some like derived categories or something like that? Because I mean, all the spooper stuff and copooper sequences, they're just an instance of triangulated structures. So probably some arguments apply in this case also.
Yeah, it's interesting. Thank you. But I know that it seems that there is a result in algebraic geometry when we in the setting of a triangulated category, but I have a plan to study this subject. But interesting question. Really, it's true that this machinery can be applied to derived categories, triangulated categories. It's an interesting question, I suppose. But I don't know. But anyway, thank you.
Okay, I think I'll pause the recording, and if someone has questions which they want to ask without recording, it's